So far we've been introduced to a few techniques on how to evaluate series, like the integral test and the nth term test for divergence. But what we want to do now is start moving into some more practical techniques, more advanced techniques. And I say practical because the integral test is really powerful, but if you have a sequence that would be very, very difficult to integrate, it's not very practical to use. However, the direct comparison test is kind of a logically equivalent way of simplifying what you have to do evaluate for convergence or divergence. Now it doesn't really tell you much about what it converges to, if it converges, but it does at least tell you whether it converges, and sometimes it's all that matters. So really the short version is this: if I've got some sequence that's a positive sequence, and I can put another, usually a simpler sequence above it, and I know that that simpler series of that sequence converges. So if I sum up those elements of that sequence, if I know that that simpler series converges, then I know that my complicated series also converges. Think about this chart here. I have kind of a complicated situation, but I have a somewhat simple pattern here. It's kind of going here and falling off. If I know that the series of that pattern, of the partial sums of that pattern converges, then I know that this complicated sequence will also still converge. And then there's an analog, and this is also a really important one, which is that if I have a sequence that's difficult to evaluate, and I also construct a simpler sequence, but I know that it diverges. So I have something that's underneath it, but I know that if I keep adding these numbers up, I'm going to add up to infinity. Well, these numbers are always larger. So clearly, if A is bigger than C, right, if each element's bigger, and these push off to infinity, then these will push off to infinity. So you can kind of think of it like a lid. If Bn is like a lid on the container, if Bn will always kind of compress down and converge to something closed, then it keeps this thing from pushing off to infinity. It can't go there because it's bounded above by this. And similarly, this is almost like a boiling of the pot. If this is the lid to the pot, and what's inside boils up and out, it's going to push that lid off. Right? So it's going to push it off to infinity. And that's kind of the basic idea of the direct comparison test. So one of the examples that you can use is I say, okay, I've got the series 1 over 3n to the 8th plus 4. Well, that's not fun to evaluate, right? I could do the integral test here, and it wouldn't be so bad to do the integral test here, but you can say, all right, well, if I think about this, 1 over 3 into the 8th plus 4, if I got rid of that 4 and just did 1 over 3n to the 8th, well, think about it. When n is equal to 1, this thing is 7, but this would only be, be 1/7. This is only 1/3. When n is 2, this thing is now 2, 3, 1 over 3 times n, they're 2 to the 8th, right? 2 to the 8th is like 256. So this is like 768 plus 4, 1 over 862. Really, really big versus 1 over 768. But if you look at it here, this is like, again, this is 1 over 768 versus over here it's only 1 over, again, 256. So this is always larger than that. And then that seems odd because you're thinking, well, wait, this is larger, but this number here is number there. Well, you have to think about the way reciprocals work, right? So think about the fact that 2 is less than 3, but 1/2 is actually bigger than 1/3. Let me say that again. 2 is less than 3, but 1/2 is larger than 1/3. Maybe it's better to say 2 is less than 4, but 1/2 is larger than 1/4. Right? So that reciprocal property works that 1 over 3 into the 8th plus 4, since this number is larger on bottom, then it's smaller and the reciprocal is smaller. If this, let me write out to be clear. If P is bigger than, so if this number is bigger than that number, and they're both positive, then when you take the reciprocal, it goes the other way. Just think about dividing this by q, side by q, and then this side by p, and you get the same inequality. Now, so that tells me if I can take what's on the bottom here and rewrite it as something simpler, something smaller than what's in the denominator here, that's simpler, I can compare that directly. So if I look at this, I say, okay, that's a p-series. Okay, well, p is larger than 1, it converges. Pfft, done, not a problem. Okay, well good, that's simple. And you can do the same idea here. You can say, all right, I have 1 over n minus 1. Okay, well I need something that's actually smaller than this. So I use the same logic. I say if p is less than q, and again they have to be both positive here, 1 over p is greater than 1 over q. So what I have to do is I have to find something where the denominator is actually larger. Well, if I just add 1 to the denominator becomes larger. So I satisfy that property. P is less than q, so 1 over p, n minus 1 is less, square root of n minus 1 is less than square root of n. So 1 over square root of n minus 1 is greater than 1 over square root of n. So what we're doing is we're manipulating that algebraically to get ourselves in a simpler situation. Now if I look at this, I say, oh, well that's a p-series. Or I could even go further and write it like that. Again, that's because so for x greater than or equal to 1, the square root is less than the actual value. So then you have the reciprocal relationship, which gives you this. So a lot of times it's easy to relate things to the harmonic series because the harmonic series is well known as divergent. This is a p-series, but you have to kind of remember, okay, for which values of p is this true, which values of p is this not true, versus if you can get it to the harmonic, you're done. Now, the problem is that this doesn't work all the time. It works in the case where I can find something convergent and do a less than, and if I find something divergent and do a greater than, but it doesn't work if I find something divergent and less than. So think about this. So again, convergent, less than, divergent, greater than. But in this case, I have a divergent and a less than. So this is less than that. Again, think I'm using the exact same logic that I used up here. I'm using the exact same logic, except instead of n to the 8th, I just have n. And this is known to diverge, but the theorem doesn't tell us anything. The fact that it's less than or equal to and divergent is not helpful. Because if you think about it this way, what you're really saying is, I've got some sequence. Well, I know that this sequence above it diverges. Well, who cares, right? Because I can always find, for like this sequence is always less than 1. Well, if I took the infinite series of 1 over and over and over, it would go to infinity. That's divergent. But that doesn't tell me if this thing shrinks enough. So this is a common mistake, so that's why I'm focusing on it. And we're going to do some more examples with the direct comparison test. But this would really be kind of your bread and butter in your toolkit, because notice in each particular case, you're using algebra skills to reduce it to something simple. Which, by the way, once you reduce it to something simple, you can then apply integral test, or again like a p-series test, or any of those sorts of things. Once you've turned it into something simple, you can apply another test, and that test might be a lot easier to figure out on the simpler sequence.